Welcome to Instrumentation for Atomic Spectroscopy. So, Beer's law requires that the line width of the light source be significantly smaller than the line width of the absorbing sample. If this is not the case, then some of the light will not be absorbed because it's outside the wavelength range of the absorption band, and in such a case, Beer's law will not apply because absorption will not be proportional to concentration. So, the line width is intrinsically limited by the Heisenberg uncertainty principle. Now recall that the uncertainty principle states that the product of uncertainties in a pair of complementary variables must be at least h over 4 pi. So delta x times delta y, or uncertainties in x and y, has to be at least h over 4 pi. It can be greater than that, but it can't be any less than that. So position and momentum is one such pair, and another such pair is energy and time. That is, the uncertainty in energy times the uncertainty in time is greater than or equal to h over 4 pi. So this delta E is the uncertainty in the energy difference between the ground and excited states, and delta T is the lifetime of the excited state, and then h is Planck's constant. So the shorter the lifetime of the excited state, that is, the lower the uncertainty in time, then the higher the uncertainty in its energy. So the lifetime of an excited state of an isolated gaseous atom is roughly 10 to the minus 9 seconds. And the uncertainty of its energy is then around 10 to the minus 25 joules. So suppose that the transition between ground and excited states corresponds to an absorption of 500 nanometer light. This energy difference then is 4.0 times 10 to the minus 19 joules. And our relative uncertainty in the energy difference then is that 10 to the minus 25 joules divided by 4.0 times 10 to the minus 19 joules, which is 2 times 10 to the minus 7. So our relative uncertainty in the wavelength will be the same, 2 times 10 to the minus 7. And that means that when we multiply by the wavelength, 500 nanometers, we get 10 to the minus 4 nanometers. So our inherent line width of an atomic absorption or emission is about 10 to the minus 4 nanometers because of our short excited state lifetime. However, observed line widths are wider than 10 to the minus 4 nanometers. They're typically 10 to the minus 3 to 10 to the minus 2 nanometers. And there are two main reasons for this, the Doppler effect and pressure broadening. So let's look at the Doppler effect. When an atom moves towards a radiation source, it experiences more oscillations in the magnetic field in a given time than one that's moving away. So if we have our atom here, if that's moving towards the light source, then in a given time as those oscillations in the electric field move to the right, that atom is moving to the left, which means that in that given time, that atom is experiencing a higher frequency. On the other hand, if our atom is moving farther away from the light source, then that atom is experiencing a lower frequency. So note here that in the reference frame of the laboratory, the atom moving towards the source is absorbing lower frequency light. Because that atom moving towards the light source will not absorb that frequency light. It needs to absorb the frequency of light at its transition energy, which means that it's going to absorb light at a slightly lower frequency as measured by the reference frame of the laboratory. And likewise, this molecule will absorb light at a slightly higher frequency. And thus the line width is increased by the Doppler effect by this equation, where T here is the temperature in kelvins and M is the mass of the atom in atomic mass units. For example, for iron with a mass of 56 AMU at a wavelength of 300 nanometers and a temperature of 2500 Kelvin, then the Doppler line width is 0.0014 nanometers. And note that this is an order of magnitude larger than the intrinsic line width is. So now let's turn to pressure broadening. Collisions will lower the lifetime of an excited state. And this means that increasing the pressure will decrease the lifetime and increase the line width. Because as we increase the pressure, we're going to increase the number of collisions of our molecules in some given time. And that's going to decrease the lifetime and thus increase the line width. So the line width from pressure broadening is similar in magnitude to the Doppler line width. And you can see here, as we go from 200 millibars to 500 millibars to 1,000 millibars, as we go from blue to green to red, we are increasing the line width of our absorption here. So A monochromator usually can't isolate lines narrower than around 10 to the minus 3 to 10 to the minus 2 nanometers. And to produce narrow lines at the wavelength of interest, then, we have to use a hollow cathode lamp that contains a vapor of the same element as the analyte. So the lamp is filled with around 130 to 700 pascal, so this is 1 to 5 torr of neon or argon gas. The cathode is then made of the analyte element, so that's cathode is here. And now when we apply around 500 volts between the anode and the cathode, then the gas is ionized and positive ions are accelerated towards the cathode. And once ionization occurs, then the voltage can be lowered such that the constant current occurs at around 22 to 30 milliamps. So cations hitting our cathode then sputter metal ions from the surface off into the gas phase, and these gaseous atoms then gain energy through collision with high energy electrons, and then they release that energy as photons at the wavelengths that are desired, because those atoms are the same atoms as we have in our analyte. They're going to emit light at the same frequencies as those frequencies that we want to come in to our flame and excite our analyte atoms. So the atoms in the lamp are cooler than atoms in the flame or the furnace are, and thus the Doppler effect is smaller in the lamp than in the flame or furnace. Also note here that the pressure in the lamp is lower than in the flame or furnace, so the pressure broadening will also be lower in the lamp than in the flame or furnace. And thus the line width of our lamp emission is sufficiently narrow to be called monochromatic to the atoms in the flame or furnace. So generally the lamp must be changed to analyze a different element, although there are few lamps with multiple elements in the cathode. So this allows for those elements to be analyzed simultaneously. So now let's look at multi-element detection with the inductively coupled plasma, the ICP. So because the ICP emission spectrometer doesn't require any lamps, a large number of elements can be simultaneously measured. So in one design, shown over here, atomic emission entering the polychromator is dispersed by the grating. So we've got atomic emission coming in, it's dispersed by the grating, and then one photomultiplier detector is needed at the right position for each element. And in another design, only one detector is used up here, a CID detector in this case. And atomic emission is reflected from a collimating mirror, making the light rays parallel. So we've got emission coming in here, we've got collimating mirror here, the light rays go parallel, they strike a prism here, and the light gets dispersed vertically, and then over here, the light strikes a grating and disperses the light horizontally. And now we have a two-dimensional dispersal of our light. It strikes another mirror and then goes to our detector. In this case, the detector is a charge injection device, or a CID. So different wavelengths are dispersed across our 262,000 pixels of our CID, again in this case. So the CID is related to the CCD device, the charge-coupled device discussed in Chapter 19. In a CCD, all the pixels were read one by one in order by row and position within the row. But in a CID, any pixel can be read at any time. That is, a pixel can be read more frequently than others to prevent it from overflowing with charge. This will reduce blooming. The charge will then be reset after each read. Other pixels can be read less frequently to build up a greater charge and thus a greater signal. Still, other pixels can be ignored entirely, saving time for reading the pixels of interest to us. So each of these increases the dynamic range of the CID compared to the CCD by allowing large signals to be measured in certain pixels, while small signals are measured in other pixels after collecting for a longer time. Furthermore, CID detectors are less prone to strong signals blooming, this is overflowing into neighboring pixels, as occurs in our CCD detectors. So here's an example of a spectrum observed by a CID. You can see that first we have this vertical dispersal of wavelengths of light, and then we have a horizontal dispersal of our wavelengths of light. And so you can see that here we're going from 224 nanometers up to 1055 nanometers. And this direction, we have labels here from 238.204 over 239.562. And so you can see that now we get this sort of constellation image where we get a lot of signal in certain areas up here. These areas are corresponding to argon signals. and then the iron signals are down here. So the disadvantage of the CID is that it's less sensitive than a photomultiplier tube, so it has a higher detection limit. However, the CID instrument is cheaper than a large number of photomultiplier tubes would be. So we have to perform background correction in atomic spectroscopy to distinguish our analyte signal from absorption, emission, and scattering from the sample matrix, flame, plasma, or furnace. So here's an example spectrum of bronze dissolved in nitric acid in a graphite furnace. And so you can see we've got some lead, we've got some iron peaks, we've got a copper peak over here. And so we've got these nice sharp absorption lines on this very broad 0.3 absorbance background. So we have to remove this broad 0.3 absorbance background in order to provide accurate absorbance measurements. So let's examine how the background can be corrected using a spectrum collected with a CID. So here we see 15 pixels surrounding an analytical peak. We've got our analytical peak here, we've got some baseline over there, and we've got a different baseline over here on this side. And note that the data would actually look like a bar graph, but in this case it's been smoothed by a computer. So the peak is represented here by pixels 7 and 8, and our baseline is represented on the left side there by pixels 1 and 2, and on the right side here by pixels 14 and 15. So the mean baseline is the average of pixels 1, 2, 14, and 15, so we simply average those two pixels and these two pixels together, and we just assume that the baseline is linear from there to there. So the mean peak amplitude is the average of pixels 7 and 8. So it's the average of these two up there. And again, it really would look like a bar graph. We wouldn't have it smooth like this. So the corrected peak height is the mean peak amplitude minus the mean baseline. So our amplitude here minus the baseline. So if our baseline is somewhere in there, we're essentially looking at the average from here to there, that difference. So in atomic absorption, we can use beam chopping to remove the signal from our flame. So as our beam chopper is rotating here, we have times that alternate where our lamp light is penetrating through the chopper to go past the flame and then onto our detector, alternating with times when the lamp light is being blocked by the chopper. And this means that now our detector is seeing, in this case, light from the lamp plus the light from the flame. And in this case, the detector is seeing only the light from the flame because the light from the lamp is being blocked. And that means that we'll get some signal where we have the light from the lamp being blocked, then we have the light from the flame and the lamp, and then we have the light from just the flame, and so on through this sort of trace. And that means that now we can subtract the contribution from the light from the flame because we know what that is when we don't have the lamp around. To remove the contributions from scattering, then we need another means for correction. The chopper is only going to remove the contribution from our flame. So deuterium lamps and Zeeman correction systems are the most common methods for this. In deuterium lamp background correction, a D2 lamp produces broad emission that is passed through the flame in alternation with the hollow cathode emission. Because the line width is so large, then only a negligible fraction of our deuterium lamp emission is actually absorbed by the analyte. It is, however, absorbed and scattered by the background, and the hollow cathode emission is absorbed and scattered by the background and absorbed by the analyte. And thus the difference in absorbance between the hollow cathode and the deuterium light is the analyte absorbance. The Zeeman effect can provide a good, albeit expensive, way of correcting the background of a graphite furnace. So when a magnetic field is applied parallel to the light path through the furnace, the absorption or emission line of the analyte splits into three components, like this. Two components are shifted higher and lower in wavelength, and then the unshifted component that remains here is unaffected because it does not have the correct polarization to absorb light, traveling parallel to the magnetic field, and thus at the analyte wavelength, when the field is off, then the analyte signal and the background are observed, and when the field is on, then that's at this wavelength here, then when the field is on, only the background signal is observed, and the difference between our two signals is then the analyte signal. So now let's turn to detection limits. One definition of detection limit is the concentration of analyte that gives a signal equal to double the peak-to-peak noise level of the baseline of a blank. The detection limits of flame instruments are the highest. The detection limits of graphite furnace instruments are the lowest. These are 2 orders of magnitude lower. And the detection limits of ICP instruments are intermediate between these two, although using ultrasonic nebulization and axial plasma viewing, they can come pretty close to that of a furnace. And that was instrumentation for atomic spectroscopy.